Chapter 7, Probability, Living with the Odds. In 7a, we'll be dealing with the fundamentals of probability, kind of talking about the basics, giving you definitions and giving you basic ideas of probability. We use probability all the time, and this lesson is going to be very practical for us in just daily living. So let's go ahead and start with the definitions. So start with outcomes. Outcomes are the most basic possible results of observations or experiments. For example, if you toss two coins, one possible outcome is HT, which means heads, tails. So if you toss two coins, one could be heads, one could be tails. I think we all can agree. But another possibility could be the first coin is tails and the second coin is heads. But also the possible outcome is you flip two coins and you get two heads or two tails. That is known as an outcome. But now an event consists of one or more outcomes that share a property of interest. For example, if you toss two coins and count the number of heads, the number of outcomes, HT and TH, both represent the same event of getting one head and one tail. So even though in this first outcome, the first coin is heads, the second coin is tails, and then for this other outcome, the first coin is tails, the second coin is heads, what do you notice they both have in common? They both have in common one head and by default one tail. So let's consider families with two children. List all the possible outcomes for the birth order of boys and girls. If we are only interested in the number of boys in the families, what are the possible events? So let's go ahead and use B to represent a boy, G to represent a girl. So that means there are four different possible birth orders. These are also known as outcomes. So you could have a situation where you have a family with two children and they have boy, boy. You can have a family situation where it's boy, girl. You can have a family situation where it's girl, boy. And you can also have a family situation where they're both girls. So those would be the outcomes. And there's four of them. Now, here's the question though. The question says, if we're only interested in the total number of boys, what are the possible events? Well, the events will be a family with 0 boys, a family with 1 boy, and a family with 2 boys. Those are the three events if we're only interested in the number of boys. Therefore, the possible outcomes when you're only dealing with boys are going to be boy, girl, boy, or boy, boy. Notice how the girl scenario is excluded only because of the question asked. Now, when expressing probability, it is very important to know that probability is going to be a very specific range of numbers, and that specific range of numbers will be between 0 and 1. So whenever you're actually calculating probability, please remember you will never get negative probability and you will never get probability greater than 1. And the reason why is because a probability of 0 means that the event is impossible. So you can't get less than impossible. When it's impossible, it's impossible. That's as low as you can get, which is 0. Okay. Now 1 means it's certain. It's going to definitely happen, and you can't get any higher than certain. So again, if you look at this range of numbers here, 0 is the least you can get, 1 is the highest you can get when it comes to probability. Please remember that. So if you ever actually calculate a probability and it's less than 0, you get a negative number, you know you did something wrong. Also, if you ever calculate probability and you get something higher than 1, then that's also incorrect. So keep that in mind. So we go ahead and look at the theoretical method for equally likely outcomes. So here's a method that's going to help us when we are actually trying to calculate what's known as later on theoretical probability. So so let's keep that in mind. So step one would be count the total number of possible outcomes. Step two, among all the possible outcomes, count the number of ways the event of interest A can occur. And then we determine the probability. The way we do that is you take the number of ways that A could occur. So that's actually step two. So step two goes here in the numerator, and then step one goes here in the denominator. So let's go do an example. Let's go and apply the theoretical method to find the probability of exactly one head when you toss two coins. So now if you toss two coins, there's actually four different outcomes. If you toss two coins, you could get 0 heads. You just get both tails. You can get one head, which is, first tail, then head. Or you can get first head, then tail. And then there's also the possibility of getting both heads. Now the question is, find the probability that you find exactly one head. Let me circle the word one. Well, that's significant because the only two outcomes that have one head in them are these two middle ones. This one here, this one here. So what's that mean? Well, what that means is there's a 2 out of 4 chance of getting one head if you toss two coins. Now obviously that reduces down to 1/2. So keep that in mind as well. So I wrote 2/4, but that reduces to 1/2. Obviously there's a 1 in 2 chance that this will occur. Now, what are the chances that when you roll a 6-sided die, what's the chances that you get a 3 when you roll a 6-sided die? Well, there's a 6-sided die. Those are the possible outcomes. Well, out of 6 outcomes, only one of them has a 3. So you probably already guessed it. You have a 1 in 6 chance of rolling a 3 on a 6-sided die. And by the way, provided that the die is fair. So now again, up here, look that the theoretical method, it's actually 2 outcomes out of 4, but that reduced to 1/2. This one just happens to be 1 possible outcome out of 6 total outcomes. Gives you 1/6. Let's try something that's a little bit more challenging. Let's say you have 52 playing cards in a standard deck. There are 4 suits. There are 4 suits. Each known as hearts, spades, diamonds, and clubs. Each suit has cards for numbers 2 through 10 plus Jack, Queen, King, and Ace. So basically each suit has 13 cards. Notice that hearts and diamonds are red while spades and clubs are black. Let's say you draw one card at random from the standard deck. What is the probability that it is a spade? So, well, there are 52 playing cards in the entire deck, right? And I'm going to pull one card out of the 52 cards of the standard deck. Pulling that one card out, what's the probability that it's going to be a spade? Well, again, there are 13 cards in each suit, spade being one of them, right? So go ahead and let's use the formula here again. It's going to be the number of outcomes that are spades, basically the number of spades, divided by the total number of cards in the deck. That's going to be 13 out of 52. 13 spades out of a total of 52 cards. This does, in fact, reduce to 1/4. And again, notice that my probability is between 0 and 1, because we all know that 1/4 is the same as 0.25. Let's do another one. Assuming an equal chance of having a boy or girl at birth, what is the probability of having 2 girls and 2 boys in a family of 4 children? Now for this one, I would recommend establishing some sort of chart. Now earlier when I talked about girls and boys, we said like girl, boy, boy, girl, whatever. This is going to be a family of 4. So because we have a family of 4 and we're also talking about like possible birth order, let's take a look at this chart. Now at first this chart might be a little bit overwhelming, but I'll explain it as we go. So if you have a family of 4 children, here are the possible outcomes. One outcome is all girls, so that's G, 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 G. One other possibility is 3 girls, 1 boy, which is this first one is your first 3 kids are girls, and then you try for that 4th kid and get a boy. This second scenario is you have 2 girls, boy, and then a girl. This third scenario is girl, boy, girl, girl. And this last scenario here is your first child was a boy, and then the last 3 were girls. But this is not asking about that. This is asking what is the probability of having 2 girls and 2 boys in a family of 4 children. So notice I have this sort of, it's this middle section here. So I have my first 2 were girls, and then I had 2 boys. My next is girl, boy, where this girl is the oldest, and then they have the baby boy. This scenario here, you have oldest is a girl, the youngest is a girl, the 2 middle are boys. I think you get the point. Okay. The point I'm trying to say is, if you'll notice, I have 6 possible outcomes where a family of 4 children will have 2 boys and 2 girls. Now, how many outcomes are possible total? Well, if you look here, there are 16 combinations possible. So if I just circle all 16, there are 16 possible outcomes total in all, and 6 of those are the outcome we're looking for. So how do we determine the probability there? It's going to be 6 out of 16, which in this case becomes 0.357. And again, notice how that is between 0 and 1. But then next, another way to determine probability is known as relative frequency. Now this actually gives us an approximation. Now you might think, well, why would I want an approximation? Well, an approximation, this is actually when you're actually doing like some sort of experiment. Okay, so there is theoretical probability, and then there is a relative frequency probability, or the relative frequency method. And it's very similar. The formula is almost exactly the same. The only difference is that we look at the number of times A occurred and divided by the total number of observations. So this is going to be done when you're doing like an experiment or something. So for example, if you're interested in only the number of heads when tossing 2 coins, let's just go ahead and look at this possible events. We're going to go ahead and toss 2 coins here. Okay. So the possible events are you get 0 heads, 1 head, or 2 heads. Now let's say we do have different scenarios where this can actually give you theoretical probability. But let's just hypothetically say you were bored on some Saturday afternoon and you decided to toss 2 coins. You decided to do it 100 times. Okay. So in this case, it's one of those things where let's say you have 0 heads occurs 22 times, 1 head occurs 51 times, 2 heads occurs 27 times. Okay, so I'm going to go ahead and compare relative frequency to theoretical probabilities. So what if you're placing a bet with a friend and you have reason to believe that maybe the coins are unfair? Like maybe your friend passed you a two-headed coin, or a coin that was weighted differently or something, because that could happen. So okay, well, let's look at the theoretical. So obviously, if you toss two coins, there's a 1 in 4 chance of you getting no heads. Because remember, we had that little picture from before, from like a few, if you go back a few slides, there was a 1 in 4 chance, a 2 in 4 chance of getting exactly one head. Well, there was a 1 in 4 chance of getting no heads, a 2 in 4 chance of getting one head, and then again a 1 in 4 chance of getting two heads. So that's the theoretical probability. But then you weren't sure that your coins were fair, so you decided to do the little experiment yourself. So how do you do the relative frequency? What you do is you take how many times you got 0 heads when you tossed the two coins, and divided it by how many times you tossed the two coins. Well, 22 divided by 100 is 0.22. Now check out, in the relative frequency, I got a different probability than I did up here, didn't I? So 0.25 versus 0.22. And then, if you're the relative frequency of one head, I ended up getting 0.51, and then two heads I ended up getting 0.27. Now notice the frequencies, or the probabilities, excuse me, are not quite the same, are they? So are the coins unfair or not? Well, the answer is no. You have no reason to suspect that the coins are unfair, because you'll notice that the theoretical probabilities and the relative frequencies are basically the same, right? So 0.25 and 0.22 are not the same, but they're close. They're pretty close. And obviously 0.5 is very close to 0.51. And finally, 0.25 is obviously very close to 0.27, right? So you have no reason to believe that they are unfair, and you can actually go ahead and continue the experiment with no problems. So there are actually 3 approaches to finding probability. So we already talked about one. The first one is called theoretical probability, which is based on the theoretical method. And so we've already understood that and seen that. The next one we've already done as well, which is known as the relative frequency probability, based on what actual observations or experiments. So you roll the die 100 times, or you flip the coins 100 times, or whatever. Now the third one is not recommended, but is known as subjective probability, and we always do this a lot. We do this a lot as humans. We try to estimate based on experience or intuition, and that's not always a great way of determining probability. Sometimes that's it's a lot of potential errors there. So I'd avoid this one if I were you, at all costs. I'm not saying don't do it, but I'm saying going with theoretical probability or relative frequency in an actual experiment is usually the way to go. So let's go ahead and identify some methods that are resulting in the following statement. So for example, this first one. I am 100% certain that you will be happy with this car. So first of all, can someone actually be 100% certain that you'll be happy with this car? Not necessarily. So obviously this is going to be a subjective method. Now I'm not saying the person is wrong. Maybe the person is correct. Maybe the person is using their experience and their intuition to make that 100% certain claim. Now, obviously, we can usually, pretty much almost never be 100% certain, but this person could be right. Maybe they know you as a person. Maybe they know what kind of cars you like, and they tell you, hey, I'm 100% certain you're going to be happy with this car. That might be subjective, but they might be right. But I'm just saying, so you got to be careful with that. So what kind of probability is this one? Which method is this? Based on government data, the chance of dying in an automobile accident in a 1-year period is about 1 out of 8,000. Well, obviously, that is based off of data. And if it's based off of data, it's based off of observations about what they've seen happen in the past. That is a relative frequency method. And then finally, the probability of rolling a 7 with a 12-sided die is 1 out of 12. That would be theoretical probability, okay? And the reason why that's theoretical is because you have a 12-sided die, you roll it, obviously you have a 1 in 12 chance of getting whatever number, any number. So 7 is just kind of a random number they picked. That's theoretical. Now, just as important as the probability of an event occurring is the probability of an event not occurring. So the way you calculate that is you go ahead and just take this formula right here. It's actually right in front of us. You basically, it's a very subtle formula, but very important formula. What you do is you take the number 1 here. Now, remember, when it comes to probability, what does the number 1 mean? The number 1 means certain. I am 100% certain. That's the number 1. Well, if you take 100% certainty and you subtract from it the probability itself of whatever event's happening, that's going to give you the event that it won't occur. Okay? Now, if that's a little confusing, let's go ahead and take a look at this quick example here. Okay? So since the probability of a family of 3 children having one girl and 2 boys is 0.375, and you can just trust me on that. What is the probability of having 3 children and not having 1 girl and 2 boys? Well, again, we're going to follow this formula here. Okay, this is the event. This is the probability that the family has 1 girl and 2 boys. So what's the probability that you have a family of 3 children and there's not one girl and 2 boys? Well, basically you take the 100% certainty 1 and you subtract from it or 62.5%. So once again, 62.5% is the event that you have a family of 3 that has a different scenario. So not just 1 girl and 2 boys. So maybe like all girls or all boys, or 2 girls and 1 boy. All right, so one other important aspect of this section is going to be knowing how to make a probability distribution. And a probability distribution represents the probabilities of all possible events. So here is the steps to doing that. Step 1 is first start by listing all possible outcomes. So we've already kind of had some experience with that in this section. And it's always going to be helpful. Well, usually it's helpful to go ahead and make a table. Next is to identify outcomes that represent the same event and determine the probability of each event. Step 3 will be to make a table and listing each event and its probability. Very important though, guys, this is actually extremely important, that the sum of all probabilities must equal to 1. When you add all possible outcomes, you get a certainty of one of those outcomes occurring. That's what the number 1 again represents, that you are certain it's going to happen. So if you add up all the probabilities of all the outcomes, you get 100% certainty of at least one of those outcomes occurring. So let's go ahead and do an example here real quick. So it says make a probability distribution for the sum of the dice. When 2 paired dice are rolled together, what is the most probable sum? And unfortunately, what this table you see before you is actually going to be something you'll have to like write out by hand many times. And it is very tedious, but it's not hard, it's just tedious. So in that sense, it's difficult because you have to like write all this out. But the point is that what you do is up here you have 1 through 6, and down here and on the side here you have 1 through 6. So we're rolling 2 die, and they're fair. Okay, and let's say you rolled a 1 and a 1. Well, take the 1 plus the 1, you get 2 as your sum, correct? Or let's do something a little more random. Let's say we rolled a 4 and a 6. Well, right here, 4 plus 6 is 10. That's another possible outcome, is that you roll a 10, I should say. And one final one, just to make sure you understand this table here. Let's say we roll a 2 and a 5. Well, we're rolling a 2 and a 5. 2 plus 5 is 7. So that's another outcome, the possible outcome of you rolling a 7. Okay, and then finally, just to really, drive the point home, again, look at all these blue ones here. For example, what if I wanted you to find all the sums of 8? Well, 6 plus 2 is 8. 3 plus 5 is 8. 4 plus 4 is 8. So all those blue highlighted ones are all equal to 8. But is that the most probable? That's what the question's asking. What's the most probable sum? Well, the answer is no. The most probable sum is not 8. The most probable sum actually is 7. Because if you'll notice, I have 1, 2, 3, 4, 5 scenarios where you have an 8. But if you look just above that, I have 6 possible outcomes that add up to 7. And actually, that would be the most probable sum. The most probable sum is 7. And because the most probable sum is 7, notice that I have 6 of these. So 1, 2, 3, 4, 5, 6. And if you take that 6, so what would be the probability? Well, the probability of rolling a 7 would be these 6 outcomes out of how many outcomes are total? Well, there's 6 elements in the row. There's 6 elements in the column. You simply just multiply 6 times 6. You get 36. So the probability of rolling a 7 would be 6 possible sums over 36 total possible outcomes, which reduces to 1 out of 6. Now, odds, as we begin to wrap this up here, odds are different than probability. Okay, odds calculate the ratio of the probability that a particular event will occur to the probability that it will not occur. So this is different. So if I'm asking you to find odds, it is not the same as finding probability. So please be very careful with this. So for example, I want to look for the odds for, like let's say I want to look for the odds in my favor. Well, then what you want to do is you want to calculate the probability that it's going to happen over the probability that it's not going to happen. And also the odds against the event are the probability of it not happening over the probability of it happening. Another way to do it is to just go ahead and count up how many events there are. That also will help you, proportionally speaking. I'll show you an example here. Now, in gambling, if you ever go to Vegas, they'll tell you the term odds on. That usually means the odds against. So if they tell you at the casino in Las Vegas, they'll say, hey, the odds on are whatever. They're telling you the odds that you will not win. So that would mean odds against. So for example, what are the odds for getting 2 heads and tossing 2 coins? What are the odds against it? Pretty simple. The odds for getting 2 heads and tossing 2 coins. Well, we already talked about this earlier, so I'll just go right to it. You toss 2 coins. There's a 1 in 4th chance that you actually get 2 heads. Now, how do I get the probability of not getting 2 heads? Well, think about it earlier. You just simply do this. You simply do 1 minus 1/4, like I showed you earlier. It's 1 minus the chances that it's going to happen. It's going to give you what it does, the chances it won't happen. That's what goes down below. Obviously, the 4s cancel in the 1/4 here, and you end up with just 1/3. Those are the odds in favor of tossing 2 coins. Now, what are the odds against it? Well, what's really nice about that is, so the odds for in favor are 1 to 3. So the odds against all you simply have to do is take the reciprocal. The odds against, you simply just flip this here, flip this fraction, and in this case you get the odds. The odds against would be 3 to 1. So that means if someone tells you at Vegas, hey, the odds on for flipping flipping 2 coins are 3 to 1, that actually means it's working against you. Let's check out another gambling problem here. Let's say you're at a horse race and the odds on, remember that means the odds working against you. The odds on Blue Moon are given as 7 to 2. So if you bet $10 and Blue Moon wins, how much do you gain? Well, again, 7 to 2 means that for each $2 you bet, you will get $7 if you win. The reason why they're offering you $7 if you win is because there's a good chance you're not going to win. So the house is betting against you, basically thinking, well, cool. If you give me those $2, I'll give you 7 if you win, because they know something. They know that Blue Moon's not very fast. But let's just imagine that you do win. So on a $10 bet, that basically means 2 $5 bets. You're going to gain $7 times 5, which is 35. Then obviously also on top of that, you're going to get your $10 back. So if you win, if you actually bet $10 and Blue Moon happens to pull one out of the bag and wins, then you actually get a $45 check on the or cash, whatever, when you collect your winning ticket.